Hello, everyone. Happy Easter. Happy that everyone is actually, several people are already starting to come in, and Kim is here and ready to go and ask questions. Awesome. Hello, hello, Kim. Hope you're doing well. I was gonna just start answering questions already, and if you guys are new to Q&As and don't know how it works, pretty much what I do is for an entire hour, I answer as many chemistry questions as possible. So if you have a specific question, like with numbers or equations, that is extremely beneficial for me because it helps me know what you're struggling in specifically. So it's easier to answer the question. Plus, it definitely helps answer, any confusion or correct any confusion that you may have. All right, so let's start off with the first question. Kim states, I'm hoping to get a preview on a workshop I will be doing tomorrow on molecular geometry using molecular models. Okay, and then so we have single central atoms and all of this. Okay, so your question is not sure how to write correctly single, let's say it's pH3. Electron domains, bonded angles. So like Lewis structures is what I'm seeing here. So Lewis structures, the main thing with Lewis structures, of course, is to understand how many valence electrons there are of each element and then properly drawing it. So let's start with this first one. So let's identify just how many valence electrons we have altogether. And then let's see for phosphorus, we know that that has exactly 5 valence electrons, and then I'm going to keep adding. For hydrogen, there's only 1, but I'll multiply this by 3. So in total, we'll get 5 plus 3, so we have 8 valence electrons. Okay, now that we know how many in total we have, and I recommend always doing that, it's counting how many total valence electrons you have initially. Now let's identify what's our central atom. So hydrogen will never be your central atom because it could only make one bond since it only has 1 valence electron. So phosphorus must be the central atom. Now I'm going to surround this with the 3 hydrogens remaining, and then we'll count up all of our electrons and see, do we have exactly 8? So let's count each one of these up. So remember that a single bond makes up 2 electrons. So we have 1 and 2, 3, 4, 5, and 6. So we're short 2. So what I'm going to do is whenever we're missing any lone pairs or electrons, I'm going to add lone pairs on our central atom. So I'll add 2 lone pairs on the central atom. This would be the correct shape for this. So that's what you're going to keep seeing. So that would have been the first example. And then let me see what else the question was. Triangular, planar. So I believe it was identifying what type of molecular shape it was and whatnot. So let's go over a little bit of what this would have been. This is based off of looking at how many electron groups we have. So let me grab my chart real quick, and then we'll go from there. So our Lewis structure chart, here we go. And then I'll see what other question we have, another multiple question there. So fine, let's see. Let me find my little chart. And I'll go from there. There we go. Okay, so for our molecular geometry, this depends on how many lone pairs there are in our central atom. So specifically with phosphorus, what I'm going to do is I'm going to see how many bonds we have. So there's 1, 2, and 3 bonds. So there's 3 bonds overall, but there's only 1 lone pair, and I'm just looking on the central atom. So whenever I'm looking at molecular geometry, then I'm just focused on the central atom, okay? So whenever you're looking at that, either electron geometry or molecular geometry. So this specific type would have been, for its electron geometry, it would have been tetrahedral. However, for its molecular geometry, it would have been trigonal pyramidal. All right, so trigonal pyramidal would have been our molecular geometry in this case. So that would have been our answer for that first one. Now for, let's see. Multiple ones, this would have been H2O2. Okay, there it is. So let me do that one, and then I'll do one more from that, and then we'll move on to the next question. So H2O2. Let's look at just once again, how many valence electrons do we have in total? So hydrogen, well, each one has 1, so I'll multiply this by 2. In total, we have 2, plus oxygen has 6 valence electrons, but there's 2 of them. I'll multiply that by 2, so plus 12. This would be 14 total electrons. for this. Now, what I'm going to do again is hydrogen can never be our central atom, so oxygen must be our central atom in this case. And a lot of times these tend to be symmetrical. So I'm going to put oxygen in the center, and then hydrogen will go at the ends. Now, let's see how many electrons we have like remaining and what we need to add and whatnot. So looking at this would have been, let's just count how many electrons. So we have 1, 2, 3, 4, 5, and 6, and we're nowhere near that 14. So I'm going to keep adding. So what I'm going to do is I'm going to add lone pairs on oxygen first, and then we'll count again and see, is that 14? So right now we have 6. So now 7, 8, 9, 10, 11, 12, 13, 14. So that would have actually been the correct setup. Now that it's perfectly has 14 electrons, that would have been the case for this structure. A lot of times with our multiple atoms or multiple central atoms, look at it as your central atoms are most likely either going to be carbon. That's the main one, by the way. Whenever you see carbon in your compound, think that that's your central atom. Or in this case, if it's oxygen. Like I said, hydrogen can never be your central atom since it could only make one bond due to that one valence electron. And then lastly, you asked about isomers. So essentially what isomers are, it's a different way to draw the same exact like molecular structure. So like think of this as we have exactly 3 carbons, 7 hydrogens, and 1 chlorine. I can draw this multiple ways and it would still have the same amount of carbons, hydrogens, and chlorine, but it's just like rotated differently. Or maybe some of the attachments are like maybe the chlorine's attached to something else. Maybe the carbon is written a different way or whatnot. So that's kind of what we look at with isomers. How I like to kind of think of it, it's basically like twins in a way. Okay, so that's one way. But what we would look at for this specific type, if we would draw this, I would start off with the carbons in the center. So this would have been carbons all throughout. And then next, what I'll do is we can put all of the hydrogens attached to our carbons, and I'll do that here. And then I'm also going to attach that chlorine at the end. Doesn't matter where you would have placed it. Let's just double check if we have the correct amount of hydrogens and the correct amount of carbons, which carbons we do. For hydrogens here we have 1, 2, 3, 4, 5, 6, 7. So that's one way. And what you're going to do, this is most likely in like either workshop or like lab class, you're going to actually put these structures together and you're going to find that you can rotate it and attach this chlorine in different carbons on different locations. And that would have been an isomer. Specifically, it's known as a structural isomer whenever you're basically taking, like, let's say this chlorine and attaching it to a different carbon. That's known as a structural isomer just because it still is the same molecular formula or chemical formula. It's just moving those bonds around or moving those atoms around. So that's what an isomer is really talking about. It'll make more sense once you kind of use the model. All right, so I hope that makes more sense, Kim. I'm going to move on to the next question. And Jose, you talked about thermochemistry. What exactly on thermochemistry? Let me know, Jose, if you have a specific question, or because thermochemistry, let me know if you want me to do like specific heat, finding heat, or I mean, the thermochemistry is a lot, by the way. There's a lot of different things that I can talk about. So let me know, Jose, if you have a specific question, and then I'll go back to your question. But I'm going to move on to another one. So we have Janine that says molecular orbital energy diagrams. I do not understand the template, okay, and how to put each put electron configurations into the diagram. Okay, and then given the NO3, okay, got it. So given the NO3 plus is a paramagnetic molecule, write the electron configuration for the NO3 plus, consider the 2 appropriate MO ladders to the model. Okay, let me go ahead and get my general like structure, and I'll explain the energy diagram from there here. All right, so let's see. Let me get my general diagram. Give me one sec, guys. Hope your Sunday is going well. For those of you here, good job for also studying and still working on this. Let's see. Okay, understanding the general idea of these. Let me grab my little chart. Give me one sec, guys. Just finding the molecular orbital chart because I do need that. Since there are different ones, and kind of like talking about these molecular orbital diagrams and charts, it's based off of like the energy levels and the orbitals that we focus on. So we will have to look at the electron configuration of pretty much each of everything, really. So we'll look at that in a second, but let me see if I can find it, because let's see. Yeah. Okay. So what I'm going to do, and this is going to be a little bit higher up, and it's a 3+ charge, I'm assuming. Let's see. Let me see what I got. It's not NO3. No, it's just NO. Okay. An O and a 3+ charge. Okay, let's see what I can do with this. Okay, so looking at, here we go. Okay. Before I even start drawing everything, what I'm going to do is I'm actually going to write out the electron configuration of nitrogen and oxygen separately, and then we'll put it all together. So for nitrogen, our electron configuration would have been that this is 1s2, 2s2, and 2p, 1, 2, 3. And then for oxygen, this would have been really similar. It's just one extra electron at the end. So this would have been 2p4. Now that we know that, what we're going to focus on is just the ending portion, or you look at the highest energy, like think of this as, this goes back to quantum numbers, like your highest energy would have been N. So essentially what we're going to look at is how we're going to draw all this out, but this is something that we're going to use. So what I'm going to do is, let me draw this out. All right, here, let me go ahead and draw this out because these take a second. So you always want to show that you're increasing our energy. And then next, what we'll show is that we'll show nitrogen and how that's building. And then on the opposite side, oxygen, how that's building, meaning using our orbitals, where are the electrons going? And then next in the center, you're actually going to put the combined compound overall. So what I'm going to do, and then I'll do 3+ in a second, but let's just do like the general template for this. So for nitrogen, this would have been 2p or 2s, and then we would have gone to 2p, and then for oxygen, same exact thing. So they're both going to have that 2s and 2p. And then what I'm going to do is I'll start drawing in the center like how this is all going to combine. And let me put this a little bit higher up. There we go. Okay. And then next what I'll do is we'll place our sigma, and then this is just representing our 2s orbital, and then this is our sigma antibonding representing 2s again, and then these are all interconnected. And then next in the center we'll have that this is sigma again, and this is pi. And let me lower this a tiny bit. And then let's see, pi again. Okay, I'm just drawing this out. This is pi antibonding, and this is sigma antibonding. All right, so what you're going to do, and by the way, on top, everything's interconnected. I just don't necessarily want to show it. It's going to get really messy. But what we're going to focus on first is, let's just look at nitrogen. And we said that its electron configuration started off with filling the s orbital, right? So I'll fill it. And then now with the p portion of this, the p orbital, there's only 3 electrons. So I'm going to fill this like this, 1 and 2 and 3. And then on oxygen, I'll do the same thing. However, it's 2p4. So this would have filled our s orbital. However, we now have 4 electrons to work with. So this is 1, 2, 3, and I'm going to come back 4. Okay. How you're going to look at this is you're going to focus at the, like, think of it as the N portion, or like nitrogen and oxygen. That tells us how many electrons we're going to combine and put in the center. So you're always adding them together. So what I'm going to do is I'm adding the bottom first. So here we have 2 and 2. That just means I have 4 electrons to work with now. So this would have filled 1, 2, 3, and 4. I'll do the same exact thing with the top portion, where here we have 3, add that together with the 4, and that gives us 7 electrons to work with and then put in the center. So here this would have been 1, 2, 3, 4, 5, 6, 7, 8. Actually, I said 7. Oop, stopping right there. So now that we have 7, this is just our typical template, okay? So now that we have, let's see, you said it was a 3 plus charge. Whenever we have a 3 plus charge, you're actually going to subtract 3 electrons from the center. So I'm going to remove 3 electrons. So here, I'll show you. From the top portion that we filled. So think of this as 1, 2, and 3 that are now gone. So that would have been our center portion of this. And then we also have to show that we removed 3. So what I'm going to do for the end portion of this is I'll show, we can state that this would have been a 2 plus, and this could have been a plus. And then together that forms a 3 plus, where I would remove electrons here, gone, and then I would remove 1 from the end. There we go. So that would have been one way to do it. You could have also done that or said that this was 3 plus for just one side, and then only remove, here, I'll put this one back, and only remove this one on the other side. So that's one way to do it. That's typically what you look at. That's how you fill it. I hope that makes more sense. With molecular orbital diagrams, start with the electron configuration, then put those at the ends, and then when you're putting it together, you're really just adding. I'm going to move on to, I'm going to come back to Jose's question. All right, so the basic system and surroundings as well as, got it. Okay, that's better. All right, so when we're looking at system and the surroundings and all of that, let's actually do a question, come to think of it. That's going to be the easiest way. But you are going to focus on, whether your Q, your heat is positive or negative, as well as whether your work is positive or negative. That's going to be a huge thing to look at. But let me grab an example of thermochemistry. Okay. Let's see what I got. Okay, so the first thing, and typically what you're asked to find is some sort of internal energy, and that sign can look like this. You might have seen this equation of internal energy or a U. They both mean the same thing, where this is Q, or heat, plus W, which is work. And both of these, as I mentioned, mean the same exact thing. So this is what they're typically talking about. This equation is what you're going to be using. And really with this, what you're going to focus on is, okay, let's look at our system. And by the way, how I want you to think of your system is whatever you're analyzing or observing. And then your surroundings are everything around your system, okay? So anything like all of the surroundings would be kind of like me right now. I would be the system. And then all of my surroundings, everything that's around me and that could affect me would be considered my surroundings. Now let's say if we had an example here where I'll state a gas absorbs 2.5 joules of heat, and then performs 13.1 joules of work. And then they're asking you to find your change in internal energy. So whenever you are absorbing any sort of heat, that means it's going to be a positive for your heat. So any single time, literally the word absorbing, or you're gaining heat. Anytime you are gaining that heat or absorbing that heat, it's going to be positive. Anytime you are releasing heat or losing heat, it will be negative. And then next for our work, whenever your system has to do work, so think of it, how I like to think of it is whenever you have to do work, it's a negative thing, right? That's how we feel. So when the system has to do work, it's negative. When the system gets work done, or when you have work done on the system, then that is positive. So when you have to do work, it's negative. Let's say you have to wash the dishes or something. It's negative. Then if you get work done on yourself, meaning maybe you get a massage, you pamper yourself, then that's positive. So that's something to kind of look at that. Now, for this specific question, our gas is absorbing that heat, so we know that this is a positive 2.5 joules. And then our system, which is the gas, is performing work, so that must mean that it's negative. So our W is negative 13.1 joules. Last thing is just add them together. So the main thing is to focus on, just to focus on, is it positive, is it negative? I think that's maybe the main question there, right? So it's kind of difficult to figure out, but that's what I really want you to think of whenever you have to do work. It's negative, even though it shouldn't be, but yeah. And then whenever it's when you get work done, that's positive. Okay. And then, like I said, all you would do is add these two together, or really technically subtract in this case. And then we would have gotten negative 10.6 joules. Okay. Cool. And Jose says, thanks. Sorry for being so bland. No problem. Just wanted to make sure I answered your question. And let's see. Yvonne states, we have how many grams of NaCl contain 1.2 grams of Na, assuming 100 grams of NaCl. Okay. So we're looking at, this is our given. And we are finding grams of NaCl. Got it. Okay. All right, so let's look at what we have. I'm going to start off with just 1.2 grams of Na, and then we're trying to change the compound to grams of NaCl. Now, I'm curious why they're stating 100 grams of NaCl. I wonder if they gave you like percent by mass, but I'm guessing not. But I'll just go with it. This would have been grams of Na. What I'm going to do is I'm going to change this to moles of Na. Then we're going to change the compound and go to moles of NaCl. And then lastly, we'll get to grams of NaCl. Okay. So one thing with this is you need your balanced equation. So let's see what we can do. Oh, they did not. Okay, no problem. No problem. What I'm going to do is I'm going to figure out what our balanced equation is, because we will need that, sadly. But this is what you would do. So since we know we are forming NaCl, think of it as it's kind of like you're going backwards and saying what should have your reactants have been. And we know we started off with Na. So chlorine exists in pairs. It's a diatomic atom. So then I know that this would have been Cl2. And then next I have to balance this out. So balancing this out, this is, I'm going to say NaCl, NaCl, and then I'll put how many of each we have on either side. Sodium, there's only one, and then chlorine, there's 2, 1, 1, and I'll place a 2 here. And then now we have 2 of each here, and I'll balance this out with placing a 2 for sodium. Okay, so that's balanced. I will need that to figure out this question, and we'll go from there. Okay, so what I'll do is I'll start off with just converting this to moles. And what we're going to use is the molar mass of sodium, which is 22.99 grams of sodium. And this gives us 1 mole of sodium. Now, our next step is to use our mole to mole ratio from our balanced equation to then change this to moles of NaCl, which helps us just change the compound altogether. So then now this would have been 2 moles of Na for every 2 moles of NaCl. And then now that we finally have the compound that we wanted, then we can continue with this and go to grams of NaCl. So we will need the molar mass of NaCl. And then, so this would have been 1 mole of NaCl on the bottom. Let's figure out what our molar mass is. So for Na, it's 22.99, we said. For Cl, it's 35.45. And we'll add those two together. Let's see what we get. All right, let's see. 58.44. That's what I'm going to place on top. And then we'll multiply straight across and divide by 22.99 times 2. You can do that, or you could even just cancel out these 2 since they divide and turn into 1. And I'll multiply this out. 22.99 this would have been 3.05 grams of NaCl, and I would have rounded up just because we start off with 2 sig figs, so this would round up to 3.1 grams of NaCl. That would have been it. Cool. So that's the main thing. Main thing was just focusing on what's your balanced equation. And let's look at balancing a redox. Okay. All right. Hello, Dolores. How to let me clear this. There we go. So we are balancing out a redox equation. One thing I did want to ask was, you really have water in there. Dolores, is it an acidic reaction or a basic reaction? So sometimes they ask you, and there's 2 different types. I'll start off doing this, however. But yeah, is it under acidic conditions or basic conditions? Let me know. I'll still start this off. Let's see. Wow, this is a longer question that we got here. Okay, and then zinc chloride. 2 KCl plus NH4Cl. What I'm going to start off with, NH2O. All right, let me go back here. Okay, what I'm going to start off with is just identifying all of the oxidation numbers for everything. So for zinc, it's 1 element in its solid state. I know it doesn't say it, but a lot of times whenever we just have 1 metal or 1 element in it, and just like by itself, that's going to be 0. And then now I'm going to move on to KNO3. So with oxygen, that's -2. I'm going to multiply that by 3 because we have to figure out what our other oxidation numbers are. What I'm explaining right now is how to balance redox reactions. Okay, so now this would have been -6, and then I'll keep going with this. So for potassium, that has to be a +1. Whenever anything is in group 1, that's going to have a +1 oxidation number. So this is 1, and then now we'll figure out what nitrogen oxidation number would have been. So here we have +1. I'm going to say +X. That's equal to the entire charge of our compound. So this is 0. So this is a neutral compound, meaning it adds up to 0 or it equals 0. That's why I'm setting it equal to 0. And then from here, let's do a little bit of math to figure out what nitrogen's oxidation number is. So this would have been 1 + x - 6 is equal to 1. Combine these 2 values together. That would have been x - 5 equals 0. So I'll add over the 5, and then x is equal to 5. So we know this is a +5. All right, all that work for just that little oxidation number. Now, the only oxidation numbers that we'll see, and by the way, this -6, after I multiplied that -2 times the 3, your oxidation number for oxygen is never going to be that -6. It's always going to be -2. So just make a note of that. This 6 was only there to help us figure out the oxidation numbers of everything else. Okay. So now let's look at this next thing. If I thought that was funny, guys. If you're explaining who's writing on the live chat, my brother helps me out. I'm not Wonder Woman, believe it or not. So now let's look at the next portion of this. So for chlorine, any sort of halogen will have a -1 oxidation number. And then for hydrogen, that will be a +1. Okay, moving on. So once again, chlorine, -1. I'll multiply this by 2, so this is a -2. Now let's identify zinc's oxidation number. So since this all equals 0, I'll state that this is x. So really, it's just going to be a +2. Keep going. And then for chlorine, again, this would have been a -1, and anything in group 1 would be a +1. And then we'll keep going. For Cl, once again, that's -1. For hydrogen, this is a +1. I'm going to multiply this by 4. So that's a +4. And now let's figure out what nitrogen's oxidation number is. Okay. And then from there, we'll look at, Dolores, you're stating it's called change in oxidation number. Okay. No problem. So I think you're just looking at whether it's changing its oxidation number. I guess they didn't tell you to balance out under acidic or basic conditions. Okay, no problem. Then nitrogen, I'll keep going with this. So this is +4 - 1 is equal to 0. I'll state this is x. and then combining our numbers together. So this would have been plus 3, and then x is then equal to negative 3. All right, these are our oxidation numbers. I'll keep going. We got one more. And let's see what else we have. So oxygen, again, would have been negative 2. These are just known oxidation numbers, guys. And then next, this is plus 1 for hydrogen. Okay. What I'm going to do next is identify what's undergoing oxidation or reduction. So looking at this, I'll start off with zinc, okay? And whenever we have a change in oxidation number where we're going from reactants to products and it's becoming more positive, that's going to be oxidation. So for zinc, this is 0 to plus 2. So since that increased or became more positive, this would have been known as oxidation. And then when we are reducing or becoming more negative really, then that's going to be reduction. So I'm going to look for what's changing, and then we'll note that here for Cl, or for, actually let's start off with K. So with potassium, there is no change. So that's not undergoing oxidation or reduction because it went from, actually didn't change at all. It just was a plus 1. And then same thing for chlorine, nothing changed there. And then same for hydrogen, no change, right, for any of them. Same with oxygen, there's no change. Everything's a minus 2. And now we'll look at what's the only other thing that did change, well, the nitrogen. So I know nitrogen went from plus 5 and then it reduced to a negative 3. So this must have been reduction. Okay, and then what I'm going to do next is I'm going to separate this into half cell reactions. So half reactions is essentially going to just be whatever's involved in oxidation. That's what I'm going to put together. And then whatever is undergoing reduction, that's the other equation that I'm going to put together. So for oxidation, and I'm going to label this as ox, and then I'll label reduction as red. Okay. So let's start off with oxidation. The only thing that's undergoing oxidation is the zinc. And then our products would have just been zinc chloride. And then now for reduction, same thing. What's undergoing reduction is this entire reactant. And then we'll just put the product as to what formed. Okay. And then from here, I'll keep going. Let's see what else we got. I'm going to add my electrons from this point. So let me go back to this. Our electrons for zinc, whenever we're looking at this, your electrons are going to be your products minus your reactants. So in this case, it would have been 2 minus 0. So we have 2 electrons. And then for your oxidation, what you're going to do with that is where you're going to add your electrons, it's always going to be on your product side. So I'm going to add 2 electrons on the product side. And then for your reduction step, you always add to the reactants. So let's look at how many electrons we're changing out here, what we're going to add. So for nitrogen, our products would have been a negative 3 minus 5. So in total, we have 8 or negative 8, but electrons are negative regardless. And then I'll add 8 on this side. Okay, so next thing is, let's see. Next thing is to figure out, do we have everything balanced? Like, let's say, do we have our zincs properly balanced? Yes, they are. Is nitrogen balanced? Yes, it is. So we're always going to look at everything other than hydrogen and oxygen. So now what we're going to state is we want to add water to balance out our oxygen. Okay, this is what you're always going to do whenever you see, and like we're specifically looking at reduction, where like this side has 3 oxygens. I'm going to add that exact amount of like waters that it needs of oxygen, if that makes sense. So since we have 3 oxygens, but none on the product side, I'm actually going to add 3 waters. Now we have to balance out how many hydrogens in total we have. So here we have 4, and then I'll distribute this. This would have been 6. So 4 plus 6 would have been 10. So on the opposite side, I'll add 10 H pluses just to make sure that's balanced. And then we'll keep going from there. Now, the next thing, after we've balanced this out, and that's why I asked, by the way, is this acidic, is this basic? I'm going to treat this under the acidic conditions. there's an extra step if it's basic. So what I'm going to do next is I always want the electrons to be the same. And right now they're not. So with reduction, there's 8. However, for oxidation, there's 2. So we want to make it into the same number. So we'll make this into 8. So what I'll do is I'll just multiply this entirely by 4. So I'll distribute that 4 into everything and rewrite it. So our new oxidation portion of this would have been 4 zinc, then going to 4 zinc chloride, and then finally we have 8 electrons. Then the last step for this is just to add them together. So this would have been 10H plus 8 electrons plus KNO3, and then NH4 Cl plus 3 waters. Okay, then let's add everything together, and then you'll note that 8 cancels out completely, which is perfect. That's what we wanted. And then from there, nothing else cancels. So we'll just add up our reactants together and add up our products. And then we'll keep going from there. So this would have been 4 zinc plus 10 H pluses plus KNO3. These are longer questions, I know. 4 zinc chloride plus NH4 chlorine, and then plus 3 waters. There we go. I fit it all there. Okay, perfect. So that would have been our answer. That's the main thing that you want to look at, is just go through those steps, oxidation numbers, see what's undergoing oxidation, reduction, break it apart into its half reactions, balance out your oxygen and your hydrogen, and make sure that your electrons are the same, add it together, and you're golden from there. All right, so I hope that makes more sense. It does take a little bit of steps, I know. Rajadeep, okay. So we have Na plus H2O, H2O, so water. And then you're asking, so you're given this and you're asking, shouldn't the products be N2O and H2? So what I want you to think of with this is, yes, it would have been technically a single replacement reaction in a way, but when we're looking at this, think of the different charges that we have, okay? And a lot of times with H2O, we're focused on this being like HOH, where hydrogen is a positive charge and OH or hydroxide is a negative charge. And then now we're going to pay attention to our charges because we want to see which ones are going to attract each other. And we know that in chemistry, the opposite charges will then attract. So now what's going to happen is, instead of this forming NaO, it's instead going to focus on combining with hydroxide. So these two would have actually preferred to combine with each other. And then from there, and it should have been H2, by the way. So this should have been H2, because these two are then going to combine, and that's where we're going to form that NaOH. And then what would be left, so this forms NaOH, and then what would be left is this hydrogen on its own. However, hydrogen is a diatomic atom, so that has to be, this has to be H2. Yeah, so that's the main thing to look at, is which charges are going to attract each other. Okay, so let's move on. How do you find the theoretical yield? So this is Sharon's question. So Rajadeep, I hope that makes more sense as to which ones are combining. Okay. And then for everyone who really wants their questions answered, I'm working on it, guys. Just to let you know, I do go in order. So that's what I'm doing right now. I have a specific order and I'm just answering as many as I can. Okay, so next to Sharon's question, how do you find the theoretical yield? So your theoretical yield is based off of your limiting reactant. So to find your theoretical yield, you first have to figure out what your limiting reactant is. So, and how you find that, by the way, it's always using stoichiometry. So let's say if you had, I'll go with this example again. Let's say if we had something like this, and we knew that there was 10 grams of Na and I'll say 10 grams again of Cl2, and then I'm asked to find what's my limiting reactant and my theoretical yield. So what you have to do is you have to figure out what your limiting reactant is by using stoichiometry. So how we'll do this is I'm going to start off with going from each grams of our reactant and then making my way to grams of product. So specifically, we'll start off with Na. Okay, so let's say 10 grams of Na. Then I'm going to convert this to, so I'm going to go grams of Na, convert this to moles of Na, then moles of my product, NaCl, and then lastly, grams of NaCl. Okay, so Na has a molar mass of 22.99 grams of Na. This is 1 mole. And then moving on, I'm going to use the mole to mole ratio for my balanced equation. So there's going to be 2 moles of Na for every 2 moles of NaCl. And then next, we'll find the molar mass again. I forgot what it was. Our molar mass of NaCl, this would have been Na is equal to 22.99, and Cl was 35.45. Add those together, and we'll see what we get. So 22.99 plus 35.45, 58.44. And I'm going to do this same sort of setup again and check the other reactant. So what we're checking for essentially is whatever reactant is going to produce the least amount of product. So that's why we have to check each reactant, how much in product it would make. And then whichever, then at the end, I'll tell you what the theoretical yield is. So let me multiply this out and go from there. So times 10, dividing everything together. So this is 25.42 grams of NaCl. That's just what our grams of, or that's just what our reactant of sodium produced. I'll do this one more time with the grams of Cl2. And then this would have been the molar mass of Cl2. So essentially that's 35.45 times 2. And then, so this would have been, 70.90? Yeah. 70.90 would have, grams would have been on the bottom per every 1 mole of Cl2. And then from there, balanced equation again. So there's 1 mole of Cl2 for every 2 moles of NaCl. And then this is still going to be the same exact molar mass, so 58.44 grams of NaCl and 1 mole of NaCl on the bottom. And we'll figure out how much that is, and we're almost done. So let's see. 10 times 58.44 times 2 divided by 70.90. That gives us 16.49, give or take. And then this is how much our chlorine produced, Cl2 produced. So what we're going to identify, what's your limiting reactant? Your limiting reactant is the reactant that produces the least amount of product. So Cl2 would have been our limiting reactant, or LR. Now, whatever your limiting reactant then produces is your theoretical yield. So this would have been your theoretical yield. Okay, that's what it always is. So the first step is to always identify your limiting reactant and then go from there. So for each value we convert to moles, yes, you do. So you're always going to go from here. This is the setup. It's always the same exact thing whenever you're starting off with grams. You're going to convert whatever they started off with. So typically they give you grams, and then you convert this to moles. Maybe they might start, if they're nice, then they'll start off here and they'll start at moles, and then you have to make your way to grams of your product. So no matter what, you're going to go from your reactant, whatever it started off with, whether grams or moles, and make your way to grams of your product. That's what I mean by this. So that's always the setup. If you have more questions on how to figure out your limiting reactant, I do have a video on it. So I really recommend that. It's it literally states limiting reactants. So check that out. And then, I also have extremely detailed notes that talk about, it's pretty much like a how-to guide for limiting reactants, how to find them, how to find percent yield, theoretical yield, actual yield, and it lays everything out in order, and it's extremely detailed. And pretty much what I like to look at it as. It's something that I personally wish I had. And I wish that the book designed it that way. So instead of using all of these crazy words and making it so complicated, I've created my own set of notes to help you guys understand the concepts and it not be so confusing. So definitely check that out. It's in the description box of this video. And also I actually created a free solubility table for you guys. So if you are on solubility or solutions, or eventually you're going to get there, make sure to download that. That is up already. So yeah. Okay, let's move on to the next question. As I take a sip of water. Okay. Whew, all right. So let's see. Malik states, what is the difference between intra and intermolecular forces? Okay, great question. So intra is talking about how the compound itself, how it's bonding, how the bonds are affecting, like, think of it this way here. I think it'll make more sense. Let me give you an example. Intra. Let me give you an example real quick. It'll make so much more sense once I draw it out. And actually, let's say if I have HCl. Or even NaCl. Yeah, there we go. Okay. So whenever we're talking about intra, we're focused on the bond that's holding together that compound. Like let's say NaCl, where we have this specific bond. Well, that would have been an ionic bond because one, it's a metal plus a non-metal that are coming together. So that's what we're focused on with like intra, is specifically looking at how those two elements are combining and then forming that bond together. So you could also think of it as let's say let's say NO, okay? Then how are we going to bond those two together? Well, this is a covalent bond now. So those specific types of bonds, that's more of looking at it as the intra forces, because that's how our, it's kind of like going back to Lewis structures, right? Where we're focused on how these two elements are bonded together. However, for intermolecular forces, we're looking at how are these Lewis structures, how are these compounds reacting or bonding to a different compound or something else? So that's the main concept behind this. Like, let's say if I were to look at metal now, and that's a positive charge, and how that's going to react with water. And I'm drawing out the Lewis structure of water, by the way. So this would have been intermolecular forces, where I'm looking at this attraction between these this positive charge and oxygen being that partially negative charge. So that's essentially, this is the difference. This is inter because it's something else bonding. It's another compound bonding or being attracted to a different compound. I hope that makes some more sense. So intra is really just within the compound, the bond within that compound itself, while inter is two different ones reacting, okay, or combining together. That's the main difference. And let's see what else I got. Okay, so Abdul asks, know how to differentiate between dipole-dipole and hydrogen bonds. What's the difference between dipole-dipole? Got it, and hydrogen bonds. So the main one to look at for dipole-dipole, anything that is dipole-dipole means it's polar. So polarity is the main concept to look at whenever we're looking at dipole-dipole. Let's say if we're focused on HCl, or water is actually a great one. So let's just look at the Lewis structure for water right now. And we know that this is polar because, one, look at your electronegativity, and we know that the most electronegative atom would have been fluorine. So fluorine's right here. So your trend is as we move from left to right on the period of our periodic table, and from pretty much as we increase on the column, then that means it's going to be increasing in electronegativity. How I like to look at it, how I like to remember it, is electronegativity. Just focus on whatever is closest to fluorine is the most electronegative, but don't think of that for noble gases. Noble gases will not have any electronegativity. They're not part of that. They're an exception to that rule. So, but like I said, anything that's closer to fluorine will be more electronegative. So that's why oxygen is then making this entire compound very, very polar. So, and plus your lone pairs on your central atom would have been polar. Now, this would have been dipole-dipole, okay? But this would have also been hydrogen bonding. And the reason for this is whenever hydrogen is directly bonded to fluorine, to oxygen, to nitrogen, and only those cases, okay? It's only going to be fluorine, oxygen, or nitrogen. Then it's hydrogen bonding. All right, so that is the main thing to focus on with that. And like, let's say if this were, I'm going to go back to HCl again. This would have been dipole-dipole because of that chlorine being so electronegative, and it is polar. However, this would have not been hydrogen bonding because it doesn't fit into any of these cases. It's not fluorine, oxygen, or nitrogen, okay? So that's the main difference. That's the main thing that you can look at. Abdul, I do have a video on intermolecular forces, so if you want to look at my channel and look for that video, that's going to help you out a lot. I even talk about pretty much all of the intermolecular forces, give you examples, and at the end I do an example question rearranging the compounds into, I believe it was increasing order. So definitely check that out. It's really, really beneficial. Okay. So let's see what else we got. Okay. What's our next question? Let me see what I got, guys. Okay, Molly asks for combined gas law examples. Okay, let me grab a combined gas law example and go from there. All right, so with our combined gas law, one, we definitely need to know our formula, and I'll show you how to use it. So let's see. Okay, so our formula for our combined gas law is P1 V1 times V1 divided by T1 equals pretty much the same thing, except it's the second portion. So that's our combined gas law formula. Now let's figure out how to use this. Now, with any sort of gas law, what I recommend doing is to I want you to automatically identify what are you given, okay? And then from there, it'll instantly tell you what gas law it will be. I love being able to see that. So it makes life a little bit easier there. Now, for our example here, we'll do the same exact thing, and I'll show you how you can just instantly tell it's going to be the combined gas law, even if they don't tell you. Got it. Have the end amount and stuff. So Molly states like how to figure out the end amount, and okay. So I'll tell you then what our given is. So let me write everything down and then put it. So for our volume 1, that would have been 17 liters. My voice is given out. Sorry, guys. Whew, okay. So much teaching these days. And then our pressure 1 would have been 2.3 atmospheres. Our temperature 1 would have been 299 Kelvin. And then always note that temperature for all of your gas laws are going to be in Kelvin. And V2 and T2. All right, let's see what else we have. So then for P2, that would have been 1.5 atmospheres. And then we'll plug everything in. So we're looking for V2, let's state, and this is 350 Kelvin. And then I'll help you out with plugging it all in and then making, doing the whole math portion of this. So let's set this all up. This would have been 2.3, and then I'll multiply this by V1, so 17, and then 299. And then next, P2 would have been 1.5, and then we're looking for V2, and this is 350. Okay. So instead of rearranging everything, what I like to automatically do is just start off with one side, okay? So I'm going to multiply these two together, and then I'll divide in a second. So we'll multiply those two values. So this is 39.1 divided by 299. And then piece by piece, I'm going to start combining as much as I can. So now, still working on the left side, I'm going to now divide those two. So 39.1 divided by 299. So this is 0.1307. And then next, I'm going to divide these two. Okay, so just to make this simpler every single time. So I'm going to divide these two values, and that's 1.5 divided by 350. That gives us 0.00428. And now this is V2. And I want you to think of this. The reason why it's just V2 is this essentially is being multiplied by V2, right? Or this is over 1 and so on. Like when you are given, oh, sorry, Molly, like when you are given an required amount and you have to use a chemical equation for required. What do you mean by that? Molly, if you have a specific example, that'd be awesome. I'm trying to understand your question. Like when you have a given and required amount and you have to use a chemical equation for required amount. You're talking about gas stoichiometry. That's what you're talking about, I believe. Here. Oh, look, okay. Let me know, because I'm about to run out of time, guys. But it might have to be, yeah, I'm about to run out of time. But what I believe you're asking for, Molly, I do think it's gas stoichiometry. That's the only time when we're using a chemical equation and we're using that to find something else. But typically you use the ideal gas law, PV equals nRT, and then you go from there. So let me know. I also have a video on, I believe I have a video on gas laws and gas stoichiometry. It was a previous live tutoring session that I did. So that's something that to look at. I'm also currently working, almost done with it. I believe I should release it by next week. I'm also working on a gas law packet that I'm making, you know, the notes that I make, I'm working on that. So definitely recommend that, but let me know. Pretty much think we're out of time, guys, but thank you so much for being here and for joining me, and happy Easter. So if you guys haven't seen my latest videos yet, and I've released 4, I've been working hard working at this. So I've been trying to release more videos for you guys since I know you guys have plenty of questions, and of course exams are right around the corner. So another thing is, on one of my latest videos, I talked about solubility tables, how to use them, and the other one was net ionic equations. Definitely check those out if you are currently on those topics. If you're currently on those topics and you're not too sure how to use a solubility table, or maybe you don't like the solubility table that you found on the internet or you were given, I recommend downloading mine. So I've done my best to make it as easy as possible. So make sure to check out that video. It explains how to use the solubility table, and it just makes life easier. And then the last thing that I wanted to mention is our beautiful community is growing, and I'm so happy that we are getting closer and closer to my goal of 10,000 subscribers. So as a gift to you guys and a thank you, is if we reach 10,000 subscribers, and with the help of you guys, of course, sharing, letting your classmates and friends know, then I will be doing an 8-hour, yes, an 8-hour live Q&A to prepare you for your finals. What? I know. So that's something that I would absolutely love to get to, and I want to help as many students as possible. That's personally a mission of mine, and my passion is to help you guys out. I absolutely love teaching. So help me get there. So if you guys can help me get to 10,000 subscribers by sharing my videos, telling your friends, telling your classmates, anyone that can benefit from this chemistry help. So definitely spread the word. And like I said, I'll be doing an 8-hour live Q&A where you guys can ask all your questions and I'll answer as many as possible. All right, guys, I'll see you next Sunday at the same exact time. We'll be doing this again for an hour, and I'll keep releasing more and more videos. So make sure to turn on your notifications to see what new videos I'm releasing and what I'm working on. All right, guys, see you next Sunday.